That's visible. Okay, so the idea behind this was to uh, carry out extensions to the. Hang on, this isn't. Let's just block through the reception. Yeah. Carry out work on extensions to the GQL graph type, which arrived in the GQL standard. There's been a lot of work going back a long way, a lot of it that started actually originally when um, I was in Neo4j and we were working on SQL PGQ, and we were thinking about what the description of a graph schema would look like for SQL PGQ. Now, as it ended up, and you've seen from Oscar, it didn't look like what GQL graph types look like, but what we were thinking about was how do we independently define a schema for the graph and then show what the mappings are from the SQL schema to a graph schema, to a more native graph schema. And then we decided from a standards perspective, we don't want to have a fight about what the SQL PGQ schema language looks like, but what we do want to do is retain the possibility of having an independent graph schema language, DDL, schema definition language. We did lots and lots of work on many aspects of this, and a lot of it didn't translate into the GQL standard, or has not yet translated into the GQL standard. So this is an effort to take all kinds of inputs. Inputs got nothing to do with that process, with other things that have taken place from other companies and other projects, and to keep going with the ideas about what a more sophisticated schema language would look like. It's an example of this GQL community work that LDBC has hosted. So you could say that schema means types plus constraints, and roughly speaking, GQL schema as it currently stands is the graph type. It's the type side of types plus constraints, and graph types only support subtyping by implication. One can work out subtype relations that exist within a graph type. And one can think about how a graph type might relate from a subtyping perspective to another graph type, but there's nothing explicit in the syntax that you use to define the graph type, nor is there any explicit utilization of the concept of subtyping from a schema perspective. And so that was something that has been of interest to, I think, to a lot of people. And Peter actually referred to this when he was talking about their type mask extension for SQL PGQ in a sense. So in late 2022, we restarted work in LDBC on property graph schema, restarted in the sense that we'd had a prior initiative called the Property Graph Schema Working Group, which did a lot of work around 2020-21 and made submissions into WG3, which I think probably had some influence on the shape of GQL. And the idea was to think about what would a schema language look like, an extended schema language, and figure out how to sort of feed that into the WG3 process so that it could be like a thinking project, a project about what might be possible for future versions of GQL. I mentioned the original work there, back at the time of WG3 contributions into SQL PGQ. There's the work from the Property Graph Schema Working Group, much of which got reflected in the PG Schema paper, which was accepted at SIGMOD last year. And then there are these things that already exist, like SQL schema or JSON schema or entity relationship modeling or UML class diagrams, and Shackle from the RDF world. And these are all sort of influences that we wanted to take into account. An example of the influence that the LEX work has had is that type keys, key label sets, which we were just discussing with respect to the Nebula implementation, came out of the LEX project. And the reason they were late breaking in GQL is because we wanted to make a contribution that would fix a couple of problems in the pre-final draft of GQL, and that's what actually happened. So in terms of direct inputs, I think I've mentioned most of these, but the thing I want to sort of draw your attention to is this diagram. Oh, you can't, of course, it's a not very visible version of this diagram. This is what we said in 2018 And roughly speaking, that's what ended up in GQL graph types. The other thing that's worth pointing out is this. A UML class diagram in ASCII art, in other words, using schema patterns, the same way we use query patterns, to actually end up at the point where we could define something that would be familiar to a conceptual data modeler. And I'll come back to that theme. Reference points are JSON, SQL, and Shackle. And there are some basic reasons for doing this, which is databases and data sets need good schema and constraints are helpful, and we all know all of those things from the experience of other database languages, and particularly SQL. But there are newer developments that actually point at the importance of graph schema. GraphRag very frequently involves processes in the tool chain that either generate schema from examination of data or utilize schema in terms of things like knowledge graph creation or query generation, and can refine the understanding of raw data that's actually being, that's in the property of the model, as it were. There's also a broader issue that goes back to, I think was most sort of fundamentally laid out by DeepMind in 2018, this paper, Relational Inductive Biases, Deep Learning and Graph Networks, which I always sort of class as the DeepMind manifesto, where they say, basically, we're moving to graphs. That's going to be the data model that we're actually using for our work. And you can see that manifested in things like AlphaFold and other products of the alpha family, as it were. Another reason I've already referred to, but I like this slide from an outfit called TypeDB, who used to be called Graken, I believe. And they say model data directly as entities with attributes and relations. It's another way of saying or pointing at the fact that the property graph data model is incredibly close to the entity relationship model. The only thing that's missing is n-ary relations. If we could bridge that gap, we would make property graph schema, property graph typing, exactly the same thing as what you do if you use any record-oriented conceptual data modeling tool. And you would stop the impedance between, the mismatch between the modeling and the actual way in which it looked in the database. And we are painfully close to actually having that bridged. And so one of the things that I'm very keen on is to actually bridge that gap, is to stop this situation where they're viewed as two separate things. Because if we can tap the knowledge of people who are accustomed to doing conceptual data modeling, it enormously increases the reach of graph data, the acceptability of graph data. There are other sort of linkages as well, which are kind of related to that. So going back to the AI theme, there are techniques like label and multi-label classification, which extremely closely correspond to things that we can do with property graphs, with label property graphs, and there are relationships also in this work to formal concept analysis, which again has an application in terms of the way in which people try and categorize and understand information in general, not just structured information. So the technical themes that we've worked on, sorry, I'm getting this mic wrong. 2023, use case and requirements, JSON schema for property types and identifying types using labels. The things we're working on at the moment are refining the JSON schema integration, PG schema integration. That means taking the things that are in the PG schema paper and actually sort of adding them into the picture. One part of that is likely to be simple keys, which are not part of graph types at the moment, so you can't put a key on a node type or an edge type. And if you logically view a node type or an edge type as being a table, which you can see in the SQL PGQ design, they literally say there's a node table, there's an edge table, but logically that is true. Then keys are obviously very fundamental. This next idea has been talked about for a long time. It's been given different names. You can think about it as having covariant schema patterns. That means you interpret your schema patterns the same way that you interpret match patterns, path patterns. If something is mentioned, let's say if a label is mentioned, and that label identifies a type, then what we want to do is say, well, if we've something is of the type person, it's also, this applies, the schema constraint or the type pattern that we're talking about applies to every kind of person, every employee, manager, student, whatever it might be. You could think about that as stating schema using supertypes. So this involves actually having a proper understanding of subtyping, or you could use the phrase that the type DB people use, which is polymorphic. They talk about polymorphic querying, and this would be a sort of polymorphic schema view. There's something that has certainly been of interest, particularly to the people in WG3 who developed the GQL standard, and that's the fact that GQL has no way of understanding the contents of its catalog. So in SQL, you have this thing called an information schema, although it's not very frequently used or implemented because it came very late to the standard. In GQL, I think there's an ambition that there should be a way of looking at what we have defined from a schema perspective as a graph, and being able to query it as a graph, being able to actually introspect, therefore, the GQL catalog and all the contained types within it. The other thing that we've just started working on, and sort of keying towards Python because of the potential utilizations in the AI space, or more generally in the data science space, is an experimental library to implement some of our ideas called GraphSchema. And future work is almost endless, the possibilities. Schema subgraphs, how they relate to transactional units of insertion, how they relate to constraints, so that we can actually say that this particular subgraph data model has to be conformed to in order for an insert to be valid, and what are the cardinality constraints or complex keys that might be associated with that. Referential integrity is not the same problem as it is in SQL because we have explicit edges. How do we actually surface the referential integrity graph? What does that actually look like? That's another schema subgraph problem. And then there's what I call shackle leveling, which is making sure that we have in property graph schema a reasonable stab at anything you can do in shackle. In other words, that you can do in RDF, because it doesn't seem that there's, there have been projects where people have actually used shackle to define constraints over property graph databases, and that doesn't seem like a particularly productive approach. So most people probably here know this, that GQL graph type is made up of node types and edge types and node types are both characterized by the record type, what we call the content type, which determines the labels and properties that can be incorporated in the graph type. So that's the sort of beginning, the foundation of what we're doing here. PG schema described things like union intersection typing for content types, and also described something which we think is very important for the graph world, which is the idea of some kind of flexible, you could think of it as an application of gradual typing, I suppose. Flexibility in terms of the spectrum of how rigid schema is, how much of the graph is constrained by a schema, how little it's constrained by a schema. Another aspect of that is the idea of open or closed types, ones that can be extended or not be extended, and that actually relates to the subtyping issue. There's two different ways of thinking about the same problem. So those are things that were discussed in PG schema. There's a fair degree of consensus given the size of the authorship list. And it would be good to actually move those into a more concrete design from a DDL perspective. We looked at JSON schema. I'm not going to spend a lot of time on this, but there's tons of stuff in JSON schema. And basically, a property graph is a graph of records, of nested records. Nested records are the same thing as documents. All of the things you can do in JSON schema, you can apply to the properties of the elements of a property graph. There's stuff that shouldn't be done in JSON schema that belongs natively in GQL. There's stuff that probably shouldn't be repeated as a completely independent specification inside GQL. That doesn't necessarily depend on the integration of a JSON data type into GQL, although that would be a good thing to do. And it's worth looking at the passage of JSON into the SQL standard to understand the sort of power of this. And it goes as far as when they brought JSON into the SQL standard, they had to standardize JSON path. JSON path is an existing language for doing path queries into document data. Why do we want to do that over again? And JSON schema sort of, has a similar role from a schema perspective. That's my personal view, and I think that that's independent of what the actual representation is, or certainly independent of any kind of storage considerations. So one of the big things you have to do here is actually define proper mappings from database data types to JSON native types. So let's move on from that. Type keys and aliases are a fact. This is a quote from my analogous presentation at the 16th TUC last year in Seattle. What it says there is what's in the standard now. The basic point here is there's a functional dependency between an identifying set of labels and the whole of the content type. If you put that in place, you can use that identifying set as an identifier. There's only one member of that set. It's tantamount to being a name of the type. That means we have the structural typing of GQL, and we've superimposed on top of it nominal typing. We haven't actually altered the type system, and we haven't altered the query language. Whether or not we ought to introduce some alterations, so some syntactic sugar, for example, on the query side, which was just being raised in Cheng's talk about the Nebula implementation, is a very reasonable question. But the idea here was to actually allow what looks like name types to exist in a world which is defined around structural typing. So information schema graph, things we're working on at the moment. You want to have a graph to represent the schema. Everybody represents their schema as a graph. If you look at anything on the internet that discusses what I'm doing with my graph, the first thing you do is you show something that usually comes from the Neo4j browser, or something that looks like the Neo4j browser, and it shows a graph that represents node types by nodes, edge types by edges, and puts labels on them. So that's the beginning of wisdom. That's a good thing to do. It's also a good way of thinking about schema validation, is whether or not we've actually got a graph homomorphism between the schema graph, between the data graph onto the schema graph. There's all kinds of advantages to actually thinking in those terms. The visualization aspect is a major one, but it's also true that if we have the schema represented as a graph, then we can do things from a query perspective in terms of looking at that graph. Now, that graph actually I don't think is in and of itself enough to represent what's going on. And so you'll see here that there are mappings shown from the nodes and edges. Well, they're not actually shown from the edges, and there's a detailed problem with that. But from the nodes and edges in the schema graph to content types. So we can say this node in this topological position has this relationship to a particular content record type. Therefore, it represents that kind of information. And that content, those content types are indicatively here organized in a type lattice. So we'll come back to that. The second part of representing everything that we know about the schema in a GQL implementation is the catalog. The catalog is a tree, nicely representable as a graph, obviously. The leaf nodes of that graph are what are called GQL schemas. They contain graphs and graph types. It's an optional part of the GQL implementation that you actually have that sort of file system organized, set up, but it's an attractive one. By the way, as a side point, one of the reasons why that was introduced was to deal with a problem that many practitioners are used to, which is all the different levels in the hierarchy of naming or labeling things within the catalog in SQL implementations. MySQL has 2 levels, the standard has 3, SQL Server has 5, or is it 6, depending on which implementation you're working with and so forth. The idea here was completely free the catalog organization from any considerations of the physical architecture of a particular database product. Going back to the actual what we map to, content types naturally organize themselves as record types into a subtype lattice based on width extension, and they slightly less naturally can have depth subtyping where the type of an individual field is a subtype of a supertype's corresponding field. We ought to be able to exploit that. There's a whole world of understanding around that, including from the FCA perspective. So there are three lattices, in my opinion, that work here. One is the content type lattice, which ought to exist independently of node and edge type applications, because then we can do things like abstract types properly. We can then have node types and we can have edge types, and we build up on those content types. If we have those structures available and we've got graph representations of them as lattices, we incorporate any and nothing to make sure that we've got that they're bounded. We have a good general way of actually representing the organization of information from a properties perspective, quite independently of the actual utilization or the application of that in terms of the topology of the graph. And so those three pieces, the catalog, and then within it, the schema graphs, and then attached to the schema graphs, mapped from the schema graphs to the content types, would give it, or node and edge types via content types or using content types, would give us a complete representation that can be brought into a graph very naturally and join together these, these interlinked subgraphs, if you want to put it that way. So the experimental library that we've started working on, the idea is to create representations in memory, the catalog, lattices, and schema graphs, but to store those graphs in some kind of embedded graph database that supports query languages. Kudzu is a natural candidate. To think about how to integrate JSON schema, and this library would be a consumer of the aspects of the TCK, which are designed to actually test the catalog and schema capabilities of GQL, and that's unlikely to come out of the work that's happening, I think, in the OpenCipher to GQL transition. So I think that's probably it. There's some papers that we've produced in the past. There's some stuff going back to 2022 as background. You can read all of that at your leisure when these slides are available. Thank you.
Any questions?
Thank you for the great talk. I have a question about the implications of graph schemas. So I'm not sure if I understand correctly, but maybe like two implications might be: first, the storage and query, they might be optimized in terms of like when we have a schema, maybe we can do something more specific. And the second is when we have a schema, we need to enforce it and check whether the data actually fits that schema. Are you aware of any existing database graph systems that already implement some kind of these concrete like implications of schemas? Or if not, what's your vision on how these should be implemented in systems?
Yeah, good questions. First of all, yes, there are definitely existing graph database implementations which are completely schema rigid, if you like. They're like SQL, and they take and inherit the benefits of schema from SQL. I think we've had an example from Nebula today. TigerGraph will be a long-standing example that's familiar to a lot of people in the community. It's the opposite end of the spectrum of from Neo4j, which historically started out as a schema-less database and has some schema features but doesn't have full-blown schema. So I think in terms of the other questions that you raised, a couple of issues. One of the things that we could do with a schema-based approach is tie it into DML so that DML would make reference to entities in the schema. So that happens automatically in SQL because you can't write an SQL query that doesn't mention table names. And as a result of that, what you can do is you can carry out incremental validation of the data, because the only thing that you have to validate against your schema ever is the validity of the data that is actually being input into a DML operation. So if I've got some tiny fragment of an update with 3 records or 1,000 records or whatever, and they've all got exactly the same format and so forth, I know all of that, and that's all I'm interested in. And if every change I make to the database is transactionally serialized from the day it was born until it's still running 50 years later, I've never actually validated the whole database, right? I never do that. It's not a database thing to do. Now, that doesn't mean that you can't use a schema the same way you would use it with a JSON document or with an XML document. And that's another use case, and it's not like it's crazy, and you get into the sort of Gen AI world and so forth, and there's lots of interesting questions about what that would look like and so on and so forth. But that's one key point, that this is actually, without schema and an attachment of schema to DML operations, so that I can say something like insert this type. If I can't do that, I can't match an SQL database for performance. But there's no reason why I can't do that, right? There's nothing inherent about graph databases that they can't use the same trick as SQL. I think that that's part of a sort of broader agenda about how do we get to the point where graph databases have enough features that their model supremacy, and I'm going to explain what I mean by that, can actually be fully utilized. So, I mean, I said that I view a table as being in a graph, a node type, which is isolated from all other node types, and therefore every instant, if I take the collection of elements of that node type, it is a table. It's a multi-set with that type. That's exactly what an SQL table is. So if I wanted to write a query that took stuff from a quota table and put it into something more complicated in the graph, that take that disconnected component and map it into something else, that's exactly what I do when I map SQL data into a graph. That's the beginning of data integration, using the graph totally, not thinking about it as two separate models. Documents are nested records. Nested records are what we have on our nodes. So we've got a model with graphs, property graphs, which subsumes document data, and it subsumes relational data, or tabular data to be more precise. I think that the issue of so you asked about the enforcement. You asked about something else as well. About the schema validation.
Yeah, I think it's basically like validation.
It is validation. Yeah. So I mean, the bigger question, the question of the efficiency of validation, and then we get into the issue of what mechanisms we would use for validation, and how we would actually carry out validation. That's beyond my pay grade, and from there'll be researchers who could have much better opinions than I do, but I think it's not the primary focus if we're looking at it from a GQL database language perspective. It is an interesting and necessary problem to address. Yeah.
Okay, maybe I also have a follow-up question. Sure. You just talked about like the schema. How to validate that schema and how to integrate it into, for example, DML. And I also want to ask, because we were just talking about like looking from the perspective of the user, we want the user to specify a certain graph schema. But what if they really don't have an idea of what schema looks like when they create a graph? So are there any efforts out there that I imagine they would probably deal with this issue from a perspective of for example, automatic schema extraction from existing graph data? Are there already some efforts out there doing this?
So that's actually one of the things we want to look at in this Grash library, is schema inference. I mean, there are some complexities because particularly introduced by the presence of optional attributes, which actually make it difficult you can't deterministically arrive at a single schema just by looking at the data. And there are also issues in terms of the coverage of the data, how big the database is. Have you got everything? Can you do it on a sampling basis and so forth? But I think that the more general aspect of that sort of relates to the point about partial schema. It's what I call the ice and water phenomenon. So one of the advantages of graph databases, and it's a real advantage, has been historically that you can just walk up and start putting data in, right? And then you get your database. It's great. You didn't have to have a schema. The problem is, as you go down the line, you discover that you can't communicate what the schema is. You can't optimize. Oh, that's the other thing you were asking about in terms of optimization. Yes, query optimization, storage optimization, all of those classic things we get out of schema. But you want schema. You want the water to turn into ice. And at some point, you want to be at 0 degrees Celsius. You want water and ice because some of it's watery and some of it's hard. Yeah, it's rigid. We know what we want. So that's part of what we're trying to do, I think, is take advantage of the historical accident that the graph database industry is divided at one pole is watery, and the other pole is ice, right? And say, how do we integrate those two things? Because they've both got advantages. And SQL forces us down this direction, and MongoDB forces us down that direction. It's probably an insult to MongoDB, and they've probably got a fully schema operating version and so forth. I'm not trying to do that, but I'm just trying to illustrate the point that we can do better than that, I think. And that is a reality for data practitioners, being able to actually have experimental data as well as having well understood, well structured data is what you actually do every day of the week. And then you have to work your way around the tools that don't support those kinds of behaviors. So, yeah, great questions. Yeah.
Thank you.
Thank you.